let's get straight into it. So this lesson is going to be about work done. Let's go over just a simple definition of work. Work is the energy transferred to an object when a force causes it to move through a displacement. Let me just get another tab open for our images. So work is a scalar quantity, there is no direction applied to it, and its unit is in joules or newtons per meter. If you were to derive it, you would see that newtons per meter is equal to the joules. So we just want to know how much energy we are giving an object when we apply a force to it. And because of that force, we can cause some sort of movement to be done. The formula for work is F cos theta times delta D, where W is the work done in joules. F is the force that we are looking at. It could be an applied force, frictional force, or whatnot. Then we have cos of theta, and theta is the angle in between the force and the displacement. So imagine this. You are moving along this line that is not letting me edit. You're moving along it, right? You're displacing as you move, move, move. Ugh, I'm gonna exit this page really quickly. Yay, it works. Okay. Oh, look here. We're moving and there's force, there's a displacement, and theta is basically the angle between the force and the displacement, or the direction of motion. So wherever you're moving, that's the angle. Sign of work. If you're doing positive work, that means that force and displacement are relatively in the same direction. And theta will equal 0 degrees since they are right on top of each other, or they are moving in the exact same direction. Negative work is when force and displacement are in opposite directions, and the angle theta is 180 degrees or more. So we can see this. Negative work. Positive work is when force and displacement or motion or what you want to call it are in the same direction. Negative is when they're in opposite. And there's also a special case when displacement is 0 or force is perpendicular to displacement or the force is 0. These are just conditions. So one of them will just make it 0 work. So one of these has to be 0. No force means you're doing no work because, yeah. No force, no displacement, same thing. And then force is perpendicular to displacement. An example is pushing a gurney. So pull out your papers and we are going to calculate this. The answer is there. Maybe avert your eyes for now. Here we are. So an emergency worker pushes a patient on a gurney 2.44 meters with a force of 15.5 newtons. So I'm going to pull out my calculator. Okay, so we're pushing a patient on a gurney, and what's our displacement? Obviously 2.44 meters, right? So we're going to plug it into this formula, 2.44 meters, and then force of 15.5 newtons, and we're going to assume they're both in the same direction, so theta is going to be 0. So we have what? Where is cos? Cos of 0 times 2.44 times 15.5, which is our force, and we will get 37.82. And do you remember the unit for this? Joules. Work is always in joules. And if we check the answer, there we go. Just make sure to consider sig figs. 3 sig figs here, 3 there. And since we're multiplying, we don't do weird decimal rules. So that is our answer, 37.8. Next, we have our force applied at 23 degrees above horizontal, so we're going to pull out our calculator, going to do the same thing, but our angle is going to be 25.3 degrees. So that, and then we multiply it by 2.44 our distance, and then again by our force, and we will get 34.2 joules. And that's our answer. So we can see that the number decreased as we increase the angle between force and displacement, so now we know that force, if not perfectly aligned with the displacement, will cause less work to be done. Here is another example you can try. So a customer lowers a 8.72 kilogram case vertically by 1.05 meters at a constant velocity. So we have a constant velocity, and we should know by now that that means the net force equals 0, right? So always look for key terms like this. Constant velocity, bam, we gotta talk about it. So we know that our applied force is equal in magnitude to gravity, but opposite in direction. We know that because it's a constant velocity, no force is overcoming the other, it's equal and opposite direction. Thus, the angle between the applied force and the displacement is 108 degrees. Why is that? We are going down, but we are applying force upwards to prevent gravity from just continually accelerating it down, so we're actually pushing it up, but we're moving it downwards, which means that the angle between applied force and the displacement is 180 degrees. And here's a calculation if you want to do that. Notice it's going to be negative. So we know that the work done by the customer is going to be negative because the applied force is going to be in the opposite direction of motion. One thing to note though is even if the object will move downwards, the person applies an upwards force to prevent acceleration, like I just said, due to gravity. That upward force is what's going to be doing the negative work. Now, I have a question for you. You ready? Let me just prepare the answer. If our applied force is doing negative work and it's going upwards, is the work done by gravity negative or positive? The work done by gravity is positive. Gravity acts downward and the displacement is downward, so the force and the displacement are going to be in the same direction. Therefore, gravity is going to be doing positive work. So let's write that down here. Gravity force. Voila! Work from force versus displacement graphs. I'm going to find some on Google right now. Force versus displacement graph. Alright, if force and displacement are in the same direction, the work done equals the area under the force versus displacement graph. We want to calculate work done. And remember how we multiplied force by displacement in order to get our work? Well, this is basically multiplying it too, right? Because we have force here, we multiply it by the distance traveled, so 6 times 2, it's not 6 times 8 because there's only 2 units here, and just consider this square for now. That would be a total of 2 times 6 would be 12 joules in this region from 6 to 8. And we can use the triangle formula, base times height over 2 to find the area of that and these. And the units of the area are in Newton meters, don't forget, which is equal to joules. Anyways, in summary, to calculate work, use this formula and use the graphs work equals area under the force versus displacement graph. Thank you so much for watching. I hope you all have an amazing day and remember to spread the kindness. Bye bye.